Welcome back to the deep dive. Today we're taking a stack of sources on vision, perception, and architectural psychology.
And we have a pretty critical mission.
We really do. We want to completely flip the script on how you think about light. We all assume good lighting is just about, quantity.
More is better.
More is better. But this deep dive is here to prove that sight is purely about the psychological power of contrast.
That's absolutely right. We treat light as this neutral, abundant resource. But the research shows perception is an immensely complicated, active process.
It's not passive.
Not at all.
Yeah.
The brain isn't just receiving a picture. It's constantly testing hypotheses about the world around you. We're looking at sources that reveal how managing contrast is the ultimate tool for controlling not just what someone sees, but how they feel and behave in a space.
So the core idea for you, the learner, is this. If you understand that vision is a contrast detection mechanism, you can stop just illuminating a room and actually start designing the human experience.
Okay, so where do we start? The physics.
Let's start with the fundamental building blocks, the raw physical nature of light itself. When we talk about visible light, we're talking about a shockingly tiny fraction of the entire electromagnetic spectrum.
It's just this narrow slice.
Spanning only from about 380 nanometers to 760 nanometers.
And just think about that for a second. That minuscule band contains all the colors we see.
Everything.
Everything else. Radio waves, microwaves, UV, X-rays. It's all the same basic physical energy, just with a different wavelength. But the effects are so dramatically different. Our entire world is processed through this one tiny window.
And understanding how that energy moves is key. I mean, we all learn in school that light travels fast, but
when it passes through anything denser than air like glass or water...
Or even your own eyeball.
Exactly. It slows down.
And that slowing is called refraction.
It is. It's fundamentally why a prism works. The light bends, and because different wavelengths, different colors bend at slightly different angles, the prism separates that single beam out.
Into a spectrum of colors, which helps us define our terms, right? Right.
So if you look at a rainbow, a spectral color is that pure, deep saturation.
Light of one specific wavelength.
And hue is just the general attribute we use in conversation. Red, green, blue. Okay, so we've got the medium. Now let's move to the receiver.
The eye.
We've all heard the eye as a camera analogy. It's useful, but it's definitely incomplete.
It's a great starting point for the optics, for sure. The lens does form a minute inverted image on the retina, just like a camera.
But the brain doesn't just interpret that image photographically.
No, and the way we collect the light is specialized for efficiency.
I found the comparison in the sources between a pinhole and a lens fascinating here.
Oh, yeah.
A pinhole image is super sharp because only one ray of light from an object hits the screen.
But what's the downside?
It's incredibly dim. You get almost no light.
Precisely. The lens is an evolutionary marvel because it sacrifices that pinpoint sharpness for overwhelming brightness. It works by collecting an entire bundle of light rays from each point of an object and forcing them all to land on the same spot on the retina. It's just maximizing data collection.
To create a brilliant image.
And speaking of the lens, here's a slightly morbid but very cool fact from the source material.
Go on.
The absolute oldest part of your body is the very center of your eye's lens.
It's true. Lens cells are added throughout life, and they push the older cells inward. As those central cells compact and harden, the lens stiffens up. It becomes inflexible.
And that stiffening is what causes presbyopia.
The loss of the ability to change shape to focus, which is why people eventually need reading glasses. It's inevitable.
Does that inevitable decline mean that our standard lighting metrics often fail for older populations? I mean, do we need to radically increase contrast for them just to achieve the same clarity a younger person gets?
That's a sharp question. And yes, absolutely. As the lens scatters more light and vision degrades, the need for clean, purposeful contrast becomes even more acute. That's a huge consideration for inclusive design.
Okay, so from the lens to the receptors themselves.
The rods and cones.
Yeah.
Named, very simply, for their physical appearance.
And they lead us to the different modes of vision, right? We have photopic vision.
Which is what we're using right now in bright light. It relies on the cones for color vision.
And then scotopic is the low light mode. That's all rods, shades of gray, what we use when we're stargazing.
And recent research suggests the importance of mesopic vision, which is this hybrid mode where both rods and cones are active, even at pretty high illuminance. But here is the critical pivot point.
The brain.
The brain.
So wait, if my brain is testing hypotheses, it means I'm never seeing the objective, raw truth.
Never.
It's always a subjective guess based on sensory signals and my prior experience.
That's exactly it. The neural signals from the retina only partially determine seeing. The brain constantly searches for the best interpretation of that incomplete data set.
So when it's always generating a hypothesis,
Then we are always susceptible to illusions.
which explains the faces or vase image or the Necker cube, we can actually force our brain to flip its interpretation of the data.
And the objective signal hasn't changed at all, just the brain's subjective explanation of that signal.
It confirms that vision is not a camera process. It's an active search for meaning.
So what information does the brain prioritize in that search? This brings us to the core finding of all the research.
That vision is contrast sensitive.
It's a detection mechanism for differences, for the figure defined against the ground.
So we talk about luminance, which is the physical quantity of light entering the eye.
The raw data.
But what we actually experience is brightness, and brightness is entirely subjective.
It's a product of three things working together.
Okay, so first, the actual light intensity. Second, how adapted the retina is adaptation. And third,
The intensities of light in the surrounding regions, which is contrast.
the famous example is simultaneous contrast. You take an identical gray square, put one on a black background and one on a white background.
And the one on the black background will appear dramatically brighter.
Because our eyes aren't measuring the absolute value of the gray,
They're measuring its difference from the average intensity of the whole visual field.
and that adaptation process is where we can really feel the mechanics of vision at work. Like when you're driving in bright sun and you go into a deeply shadowed forest.
You feel that massive lag. That's your cone system struggling to catch up.
But we need to differentiate the rates. Cones, which handle color and daylight, adapt pretty quickly.
About 7 minutes for light adaptation, like when you leave a dark movie theater.
But the rods, our dim light sensors, they're the slowpokes.
They take an hour or more to fully achieve dark adaptation. That's why you can't see anything for the first 10 minutes when you enter a dark cave.
This difference in sensitivity between the rods and cones also creates the famous Purkinje shift.
Right, where the colors that look brightest actually change as the light level drops.
In bright light, our cones are most sensitive to yellow-green.
But in low light, the rods take over, and they are most sensitive to the pure green part of the spectrum.
Wait, that's huge. So the implication is that if you want subtle emergency lighting in a completely dark environment, or if you want to preserve your night vision.
Green is the most effective color. Our rods are highly tuned to it. It's an evolutionary tuning that dictates our safety protocols.
And the brain isn't just adapting to light, it's actively fighting against the instability of light.
Which is where color constancy comes in.
This is the brain relying on stored knowledge, right?
Yes, we expect a ripe banana to be yellow. We expect grass to be green. The brain uses context, form, and expectation to maintain a stable, constant perception of color, even if the actual wavelengths hitting the retina are wildly different.
So the brain is actively filtering out the light source? A white candle looks white when you see it in a dark room.
But you put it next to daylight and suddenly the brain shifts its reference point.
And the candle appears yellow. The perceived white is always shifting relative to the brightest available light source.
This reframes the entire discussion, doesn't it?
It really does. If the brain is compensating this much for the light source, and if vision is fundamentally contrast-based, then the manipulation of brightness contrast must be the primary driver of emotional response in any space.
That's the leap the sources make. Engineering often focuses way too much on achieving uniform illuminance metrics on, the work plane.
But that lack of contrast, that uniform shadowless lighting, it's detrimental. It mimics a sterile, cloudy day.
And the studies show that chronic exposure to that low-contrast uniform illumination causes people to feel listless, even depressed.
So the creative goal isn't to wash the space in light, but to design the feeling of a sunny day.
Sharp highlights, crisp shadows, and defined contrast. But the appropriate level of contrast depends entirely on what you're asking the person to do.
Which leads us to environmental psychology and the concept of cognitive load.
We talk about high load and low load environments.
High load is complex, crowded, novel, asymmetrical, like a bustling neon-lit city street.
And low load is the opposite. Simple, organized, symmetrical, and familiar like a quiet, minimalist library.
And you have to think about the synergy between the task and the environment.
Okay, so if you're performing a complex task-studying technical material for an exam, That task already creates a high degree of arousal. It's high load.
Right. And if you try to do that in a complex, crowded environment,
The combined stimulation is too much. You hit sensory overload, and performance drops off a cliff.
that's why we instinctively seek out quiet, low stimulation environments for deep, concentrated work. Complex tasks benefit profoundly from a low contrast setting.
Diffuse, even shadowless light that minimizes visual competition.
But conversely, simple or routine tasks like writing checks or familiar chores are inherently low load.
They're unstimulating, they're boring.
So these tasks benefit from a mildly stimulating high load environment.
Which explains why people will often migrate to stimulating rooms, like a busy kitchen, to do their routine paperwork, or why they'll put on energetic background music while doing monotonous chores.
The environment needs to provide the stimulation that the task lacks.
So if you want a behaviorally neutral space that supports difficult, sustained visual tasks, you need a low contrast environment. You achieve that with a high proportion of diffuse, shadowless light.
But if you want to command attention and evoke specific moods, you need a high contrast environment.
Which means a large amount of focused, sharp light and very little diffuse light. This establishes a clear hierarchy foreground versus background, and it guides the eye.
Like a single spotlight on a dramatic stage.
This functional application of contrast was poetically crystallized by the master lighting designer Richard Kelly.
He identified 3 fundamental elements.
That determined the emotional setting of any illuminated space.
First up, ambient luminescence. Kelly called this the snowy morning in open country, or the twilight haze.
It is the ultimate low-contrast element. It's shadowless, it reduces form and bulk, and Kelly famously said it dematerializes things. Because everything is equally important or unimportant, it's perceived as reassuring and restful.
Then we have focal glow. This is the critical element that introduces contrast.
This is the campfire of all time, or the single sunburst cutting through the clouds.
Focal glow commands attention.
It fixes the gaze, and it's the element that actively organizes the space by separating the important from the unimportant. It establishes a hierarchy. It's used to induce movement and control circulation.
So if ambient is the canvas and focal glow is the spotlight, the third element is the emotional punctuation mark.
Sparkle, or the play of brilliance.
Kelly described this as the cache of diamonds in a cave, or stars in the heaven.
It's the microscopic bombardment of light points. Sparkle is purely stimulating. It excites the optic nerves, it heightens all sensations, including appetite, and awakens curiosity.
Now, these elements are elegant in theory, but they were confirmed through hard science by Professor John Flynn.
He conducted these classic experiments where he took a room and used 6 different lighting schemes without altering the physical structure at all.
And he proved that different patterns of brightness contrast consistently alter our subjective impressions of the space.
Flynn categorized the effects into 3 groups. The first is spaciousness.
So impressions of largeness are fundamentally tied to light intensity and uniformity.
Specifically, higher illuminance, particularly when focused on the room perimeter, makes people describe the space as clear, bright, distinct, and
More spacious. The brightness around the edges visually pushes the walls back.
the second category is perceptual clarity, which often defines how public or private a space feels.
So high general illuminance increases facial clarity. It makes people feel connected, reduces anonymity, and encourages intermingling. Very public.
But if you introduce shadow and silhouette, you inhibit the ability to perceive precise facial detail, which reinforces detachment and privacy.
That's why you see focused, shadowing light used in crowded, high-end cocktail lounges or fine restaurants. It visually separates people even if they are physically close.
And finally, pleasantness. Flynn found that the non-uniform brightness from downward concentrating lighting, which inherently creates contrast rates much more favorably.
Friendly, pleasant, sociable, and interesting, all compared to the diffuse, uniform, shadowless systems.
So the ultimate takeaway from all this research is the absolute need for variation.
Static, unchanging settings lead to monotony, which quickly breeds boredom and even depression. We need change.
Which means that in environments built for high-load tasks like offices or factories, the break areas must be designed with greater contrast and sparkle than the primary workplace.
That change provides relief and that essential low-load stimulation before workers have to go back to concentrating.
We've moved from that 380 nanometer slice of the physical world to Richard Kelly's poetic genius and the scientific proof offered by Flynn.
This deep dive has shown that effective design is not about drowning a space in light. It's about surgically managing strategic contrast to generate precise emotional and behavioral outcomes.
And this journey always circles back to the brain's constant quest for the best hypothesis. We've discussed constancy, how your brain tries to keep the world stable based on stored knowledge.
So, given that light constancy, color constancy, and visual memory are so heavily based on what the brain expects to see.
Here is the provocative thought for you to chew on. When you walk into your familiar kitchen tonight, how much of what you see, the brightness, the color, the definition, is actually dictated by the light present?
Hmm.
And how much is simply your brain filling in the blanks based on decades of past experience?